L equals T minus U. So it's kinetic energy minus potential energy. And then what I did was I solved for the total velocity. And so I just found the tangential components of the wheel's velocity in the x and y direction, and then the velocity of the pendulum in the x and y direction. And then I plugged in omega equals 0, so if the wheel were not spinning at all, it would just be a normal pendulum. And then I also plugged in, well, I got it simplified down to just the velocity of the pendulum, which is good. And then I set phi equal to 0, so Vp should equal 0. And then I realized that I needed an expression for Vp, so I just used forces and got the Vp equals gt plus v naught p. That's the total velocity of the pendulum, so that will be broken down into x and y. So this is my expression for velocity, and theta dot is just omega. Theta is this angle here between r, here, you can see it better here, between r and the initial position. And then I plugged everything into the Lagrangian to get this whole change in height thing. I called this potential energy is 0, so this height is r plus L, and for the height at any given time I subtracted the height here, the difference between this, so if you just had a normal pendulum, and that was L minus L cosine phi in this case, and then also this loss of height here, which was just r sine theta. And then to put it into the Euler-Lagrange equation, I found dl d theta. It should be equal to d dt of dl over d theta dot, and the same for phi and phi dot, but we don't have any phi dot terms, so phi dot is 0. So I just found the derivative with respect to phi and got to this, so that's our expression to find phi. And then I found dl d theta, I just took the derivative, and then dl d theta dot, and then d dt of dl d theta dot, and I set this equal to this and simplified a little bit and got this expression, and this is just a simplified expression for my phi equation.